What if I told you that the key to understanding the universe was a tiny particle, which is nearly impossible to detect, so much so that they are even called ghost particles? They don't obey traditional laws of physics, they barely have mass, and they outnumber everything else in the cosmos. Oh, and there are trillions of them passing through your body right now. They do exist, and they're called neutrinos. This brings us here to the Caucasus Mountains here in Kabardino-Balkaria, where we're going to visit the unique Baksan Neutrino Observatory. And it might surprise you, we're not going to find it out here in the open, but instead, we have to go about 2 kilometers deep underneath this mountain range. Very simply, what is a neutrino?
Some physicists call neutrinos the ashes of the universe. We will now have to travel 3.5 kilometers inside the mountain. We live in a sea of neutrinos, so we could take a swim.
Our entire fundamental understanding of physics is wrong.
We can't rule out that we're dealing with something else, something entirely different, a different kind of physics. We pretty much always have more questions than answers. Whoever wants to see the results of his work immediately should become a shoemaker.
Vladimir, thank you very much for hosting us here today. Very simply, what is a neutrino? How far deep are we going into the mountain, and why do we have to go underground to see them?
Some physicists call neutrinos the ashes of the universe. They're produced as a result of a low or extremely high energy release. Our observatory is deep underground due to the huge amounts of energy that impact Earth from space. Cosmic rays create interference, and that would prevent us from detecting the neutrinos. So we go down far enough to where neutrino interactions are still possible, despite some remaining background cosmic radiation. We will now have to travel 3.5 kilometers inside the mountain, and there will be the equivalent of 4,800 meters of water above us in the lab.
So how are neutrinos made, and do they last forever?
Nothing is eternal. However, we can't rule out that neutrinos are precisely that, eternal particles.
So there are more neutrinos than anything else that we know of in the entire universe. Why do we know so little about them?
There are so many things we still don't know about, and we're happy to be learning more about this phenomenon. We know now that neutrinos play an essential part in our universe.
Are we ready to go inside?
Yes, go.
So this is actually a telescope, but in my eyes, it looks nothing like a traditional telescope. From what I understand, you can actually catch a glimpse of a neutrino. How does that happen?
You are absolutely right. This telescope is very different from the traditional kind. This is one of the methods to find a material that interacts with neutrinos just slightly better than others. It hardly interacts with anything. This telescope was specifically designed to study neutrinos emitted by the sun. What for? There's a pattern to how all stars work, and the sun is no different. Neutrinos are born in the core of a star, with a massive release of energy. Inside the sun, for example, the temperature is 14 million degrees Celsius. And when neutrinos reach the Earth, you can detect them if you shield the lab from all other influences. We are now in an underground lab at a depth where the flow of cosmic rays is reduced by several digits. The sun is a giant ball of matter that gives birth to neutrinos at its very center. They escape the sun into space, and 600 billion neutrinos per square centimeter reach the Earth every second. Neutrinos pass through us, too. We live in a sea of neutrinos. In order to detect neutrinos passing through something, you have to remove everything else to clear the way. Because loads of cosmic radiation, or cosmic rays, reach our planet. The atmosphere's upper layers protect us from cosmic radiation, and the energy which finally reaches the surface is harmless. At the same time, this is a major obstacle for studying neutrino interactions. We have to get away from everything else that reaches Earth by going underwater or underground. Right now, we are deep underground. As a rule, the distance to the surface is measured in meter water equivalent. Right now, we are shielded equivalently to the depths of 4,800 meters below the surface of a body of water. So we could take a swim.
Okay. So once you see a neutrino, how do you get it to talk to you? How do you get information from it?
How can we capture neutrinos? Or to be more precise, how can we establish that a neutrino has passed through? We have to find a substance that interacts with neutrinos more than any other type of matter. The first researcher to discover such a substance was Bruno Pontecorvo. He is known for a response he gave to Wolfgang Pauli, who introduced the term neutrino in order to maintain the fundamental law of the conservation of energy. When Pauli said, "I suggest that a particle, the neutrino, carries away some of the energy emitted in radioactive decay," but that was the wrong thing to do because researchers will never be able to detect that particle. And Pontecorvo replied, "That's not true. We can and will detect it. We need to take a large amount of substance." And he actually named the substance, chlorine-37, one of the isotopes of chlorine. The neutrino, some minuscule part of it, will interact with chlorine and turn it into argon-37. It's a noble gas, and it's radioactive. You have to collect it, and then you can determine how many neutrinos were captured by the chlorine. That was done very well by Ray Davis. We worked together with him on creating this device, and he shares the credit for this project. It was before he won the Nobel Prize. He received it later. So it turned out that chlorine can only interact with high-energy neutrinos. And based on our calculations for the Sun, only a small part of neutrinos are like that. This triggered further research to find a way to detect neutrinos. One of our researchers, the late Dr. Kuzmin, discovered it. He suggested using gallium, and it proved to be effective in detecting low-energy neutrinos that are generated by the Sun in abundance. To be exact, 99% of all Sun-generated neutrinos. If we use an analogy, the Sun is more like a compost heap, where the organic waste undergoes a slow process that generates heat. If we look at how neutrinos are generated, it happens when protons and neutrons from hydrogen atoms are merged into alpha particles or helium atoms. It's a slow process, and it doesn't occur often, but as the Sun consists of hydrogen and helium, the process goes on. The Sun continues to generate heat as long as the balance is maintained. It's interesting to note that the light, gamma quanta, is born at the same time as neutrinos. It takes 14 minutes for a neutrino to reach Earth, but gamma quanta can linger in the depths of the Sun for thousands of years. The rays reaching Earth now were actually generated 1,000 years ago, while the neutrinos have only just been produced. Their generation is a very steady process. The Sun can be turbulent, it can release solar flares and so on. But that's all surface phenomena. The core, however, is very precise, very stable. And I believe the Sun will sustain us for quite some time.
So the gallium-germanium telescope gives us information coming from the Sun. You've already touched on this a little bit. What kind of specific information can we get from this telescope?
First of all, we have a confirmed understanding of the Sun and all the processes in it. Not all of our questions have been answered yet, but that requires much higher precision. We're planning to replace gallium with a scintillation detector, a massive one. Telescopes like that are already being built in some laboratories, for example, in China and other nearby nations. When it comes to the Sun, with the SAGE experiment, we're seeing a constant process and not much is changing. Now we're more interested in the neutrinos it emits than in the Sun itself. We register twice as few neutrinos as theoretically expected, considering the amount of energy released. So the next step would be, there are three types of neutrinos: electron, muon, and tau. The Sun only emits electron neutrinos, although a wonderful theory has recently suggested that neutrinos change their flavor. Physicists are lyricists as well, you see. So neutrinos can shift from electron to muon or tau and vice versa. This phenomenon is called neutrino oscillation. Our telescope can only detect electron neutrinos. So this change of flavor explains why we register only half of the Sun's neutrinos.
This is the Underground Scintillation Telescope. It is the size of a 4-story building, and it is covered from top to bottom in particle detectors. And it is sending information to computers, which is allowing scientists to monitor the movement of neutrinos in real time. Mark-Thier, thank you very much for having us here at the Scintillation Telescope. If I understand things correctly, here we can witness what neutrinos are doing in real time.
Yes, we monitor neutrino events. Two types of neutrinos: electron neutrinos, particles produced during a core collapse supernova explosion, and muon neutrinos from stars and other cosmic bodies.
So tell me, what are we looking at here? What is this, and what does it do?
This detects and registers cosmic rays. Its shape is reminiscent of a large cube, but it has 8 planes, not 6. They consist of scintillation recorders. Scintillation is a process where a charged particle passes through a sensitive material, which emits light upon interaction. So here, the charged particle passes through scintillation recorders and particles of light appear. There are special lamps under these black covers that intensify this, and they are converted into electron signals. These signals go to the machine room. By analyzing the sequence at which the signal reaches the control room, we recreate the trajectory of the particles. That is why this detector is called a scintillation telescope, because it can trace the trajectory of the particles through scintillation.
What is the furthest back you've been able to trace a neutrino from, and how do you actually trace it back to its origin?
This detector can register 2 types of neutrinos. The muon neutrino traverses our whole planet, interacts with the soil under our detector, and then the muon goes up. Since cosmic ray muons travel down, and this one goes up, we can separate it and know for sure that it's from a neutrino. So, we can say that we've registered a neutrino from the other side of our planet. But these neutrinos not only cross the universe, they come from our Earth's atmosphere too. So we can't be 100% sure about the source. But we can compare the coordinates that we get with the coordinates of a celestial body. As for electron neutrinos, they are weaker. The particles that appear after interaction don't go further than the detector. So we can't trace the trajectory. Single neutrinos would be impossible to register like those muons. But we can detect a big neutrino flow. Like I said, the detector has 8 planes. It looks like a cube on the outside, but there are 3 planes on the inside, 1 on the bottom and 2 additional floors. These internal planes are protected from the muons by the outside walls. And this internal section has a low background. We observe single reactions on these detectors. We call that a background. When a collapse happens, where the detector can sense it, the number of reactions increases. We use it as our benchmark and calculate the flow based on this discrepancy. We can calculate the flow, but we can't see the trajectory. We need optical or radio telescopes for that. A supernova is a very rare event for our galaxy. The last one happened in 1987 in a neighboring galaxy, the Magellanic Cloud. The event was registered by 4 detectors, including one of our own.
Let's say a star in our galaxy goes supernova. It will be disastrous for us, presumably. Would we be the first to know about that here at this telescope? And if so, what is the process that goes into play once that detection happens?
A supernova is a stage in a star's evolution. The star must be 3 times heavier than the Sun. To put it in simple terms, its core burns out and turns into metal. This causes a massive collapse. The reactions that follow make electrons and protons disappear, and large amounts of neutrinos appear as a result. The massive impulse is sent in different directions. It lasts for about 15 minutes. The detectors we have on our planet begin to react, and we witness either single reactions, like in our case, or spikes, if you have a different type of detector. Such detectors can also register the direction it's coming from.
Well, it's fascinating. Thank you very much for taking the time to show me around. Scientists at this observatory have been making headlines with the best experiment on sterile transitions. They may have discovered a brand new elementary particle, the sterile neutrino. So, first of all, congratulations. This is a big deal. What does this mean for humanity? Why should we be excited?
It's hard to speculate on the implications of that discovery, but humanity strives for every drop of novelty and mystery. This particle isn't new, but it is a new type of neutrino.
So, my understanding is that the best experiment could mean that our entire fundamental understanding of physics is wrong. Are we in for a new era of physics?
It's fascinating, sure. We always enjoy discovering something new, and I hope we've come across something exciting. Maybe it's not a sterile neutrino, but new physics indeed.
Now, one of the big questions about physics is the evidence of dark matter, and we don't really have any evidence per se. Can your experiments here with the BEST observatory help us find out more information about dark matter? Can sterile neutrinos give us more insight into this?
Yes, absolutely. Dark matter is a real mystery, and any new information, including information about neutrinos, could help us solve that mystery.
Science happens on different scales. The BEST experiment here is relatively small compared to something like the Large Hadron Collider. Is there a benefit to working on a small scale? Tell me about the pros and cons.
There are always pros and cons to any research, but we'll keep on working and moving forward. First of all, I'd like to say that the BEST experiment was successful thanks to the continued cooperation with our fellow researchers from the United States. We value that cooperation highly, and we are very happy that they worked with us on the BEST experiment to produce some very interesting results. While we searched for possible oscillations between active and sterile neutrinos, we can't rule out that we're dealing with something else, something entirely different, a different kind of physics. We're now preparing a new experiment that will either help us find an answer or perhaps leave us even more puzzled. We pretty much always have more questions than answers, but we're going to keep up our work, and we hope to finally get those answers.
So we're starting to see more neutrino observatories starting to be developed ever since your discovery about the possibility of sterile neutrinos. Do you think that interest in the sphere is starting to increase?
We expect it to, because neutrinos are associated with many interesting problems, and solving them could really advance our knowledge about the world, which is why it's among the hottest research arenas in fundamental science right now.
So we know that the Baikal Deep Water Neutrino Observatory has witnessed an explosion from blazars, which are from different galaxies. What can we find out from what's happening out there?
Yes, we were very lucky. And what's particularly important is that both the Baikal and the Ice Cube neutrino telescopes detected these neutrinos coming from a blazar. So we can rule out any possible errors here. It's a real gift for us. As researchers, we need all the incoming data we can get. I hope there will be more events like this so we can continue this fascinating, cutting-edge research.
Given that neutrinos have mass and that there are so many of them, if we are able to understand them more, are there practical uses for neutrinos if we can learn to use them, maybe as an energy source or even possibly high-speed internet because they don't have to go through any barriers?
Russian researchers have developed the best artificial sources of neutrinos, that's a fact. And we plan to develop more. And it should be noted, the research options in this area are quite limited, since there are only 4 or 5 elements that can be used to create artificial neutrino sources. Also, all nuclear reactors generate anti-neutrinos. Although they're not the same as neutrinos, they are just as valuable to physicists. I can only say that neutrinos can carry information about various processes, so many of them haven't even been researched yet. Speaking about the practical applications of neutrinos as sources of energy, I would quote Einstein. Whoever wants to see the results of his work immediately should become a shoemaker.